Hello everyone, my name is Damitha and I'm here to present GALA, a graph neural network or GNN domain-specific language and compiler. So let me start with the very basics. A graph is a collection of nodes which represent entities, and edges in these graphs represent relations between these entities. You find graphs in many real-world applications. I don't need to give many examples, but to just give a few, it's used in chemistry to show bonds between chemical compounds, as well as it's used in social or research networks, etc. So let's try to answer a question using this network. Let's say that given some person here, we ask the question, what is their next research topic area? Intuitively, as we all know, it's not only dependent on oneself, but it's also dependent on the interests of the people around you. So given that we want to apply some data-driven solution to this, what can we use? And one example is a graph neural network, which is basically a neural network that functions on a graph. And thus, it also has neural network operations, such as a feed-forward neural network, as well as nonlinear operations such as ReLU, etc. These operations are typically lowered down into dense matrix operations. And conversely, you also have graph operations such as message aggregation, where messages are passed between nodes, and finally the result is aggregated in the end. There are also operations such as graph attention, which functions on the edges of the graph to produce a attention result. These operations, on the other hand, are typically lowered down into sparse matrix operations. And this sparsity brings a very interesting challenge, namely this irregular sparsity, which sets graph neural networks apart from most other machine learning workloads. Whereas you see here, you have different adjacency matrices for the two graphs that are seen here, and having different varying non-zero distributions or edge distributions. This can make optimization a very input-sensitive challenge and also a very interesting one. And capitalizing on optimizing for this sparse workloads, we have sparse tensor systems such as sparsity-IR as well as TACO. These systems mainly focus optimizing on what we call a intra-operator level, which is optimizing at the level of a single operation or a single data structure. For example, optimizing sparse matrix multiplication kernels. Meanwhile, you have systems dedicated for graph neural networks. These systems, such as DGL and its compiler GraphFiler, focus optimizations on the more inter-operator level, which is spanning optimizations across multiple operations. Some examples include operator selection as well as operator reordering. But what we found is that there is a missed opportunity here. And that is that most existing systems don't really optimize both at the inter and inter-operator levels. Let me show you why this is important. So what we see here is our own implementation for a two-layer GNN model applied to the graph dataset, where you see the adjacency matrix on your left. On the y-axis, you have various optimizations applied, and on the x-axis, you have runtime. So the shorter the bar, the better. What we have first in gray is an unoptimized implementation, which we then apply various intra-operator optimizations, which you see here in yellow. This leads to a total speedup of 1.6x. On the other hand, when you only apply inter-operator optimizations, such as operator reordering, we see a total speedup of 5x. When all of these are combined together, we see a speedup of 10.3x. But hold on. Did you notice something very interesting here? The intra-operator optimizations, which have a speedup of 1.6x, and then the inter-operator optimizations, which have a speedup of 5x, when combined, you are expected to see a speedup of 8x, their product. But the actual speedup is much higher, showing that there is a synergy between the optimizations. So exploiting on this, as well as two other opportunities, we created a solution. And this solution lets us achieve significant speedups over many existing baselines for both inference as well as training. And that solution is GALA. GALA comprises of three main parts: the language, the intermediate representation, as well as its automatic transformations. In the interest of time, I'll only be going through the intermediate representations in depth. I encourage you all to go read the paper for the details of our other components. But just to give a gist of some quick insights on the language and automatic transformations, the language is designed with a separate algorithm and schedule similar to languages such as Halide, and it's used specifically and this is used to specify intra-operator transformations by the user. Meanwhile, we also perform automatic inter-operator transformations that are almost always beneficial using the information stored in our intermediate representations. And going back to these intermediate representations, let me show you how we build them. So given some statement in our front-end language, we first store the details regarding the computation operation itself in what we call our compute IR. In this case, this is the aggregation operation across nodes, which we show here below. We store the details, such as the operation type, as well as the underlying computation, along with maps to the input and output data, which we store separately in a separate data IR representation. In addition to these two details, we also store the intra-operator transformations that are specified in the scheduling language of GALA. These are shown in blue here. And so, for example, the sampling and coarsening transformation specified in the compute IR node is used to generate a transform aggregation kernel during the final code generation. And likewise, we also perform column tiling transformations, which tiles the graph, which is specified in the data IR. What we have noticed, and which also influenced our design to have separate compute IR and data IR, is that these transformations, which happen at the intra-operator level, can be performed in isolation. This enables the separation of concerns, making it much more easier to perform intra-operator transformations, as we've shown here below. But there is structure to these IRs. They are not independent blocks. For example, the compute IR is a sequential representation of compute operations, which stores the computations in the GNN model in a layer unrolled view, which gives it a global view of the entire program. On the other hand, the data IR is a graph representation, where you store relations between data objects as edges in the graph. And these edges can store relations such as input-output dependencies as well as transformation dependencies. We use these additional features to perform our automatic inter-operator transformations, which include training-aware subgraph creation, sparsity-aware rewrite rules, training invariant code motion, as well as complexity-based operator reordering. In the interest of time, again, I'll only be going through the training invariant code motion transformation, which is essentially loop invariant code motion, where the loop in this case is the training loop. And any operation that does not give different outputs across the training iterations, we just move it out of the loop. So let's see how we find such operations using the IRs as an example. We first take the operations in our compute IR. So this one here. And then check the mapped inputs in the data IR. So once we go to the data IR, we then trace back through the relations stored to see if any input is dependent on any learned weights, which then contribute to the changing results across iterations. So if there are no dependent learned weights, then we can, which is the case in this scenario, we simply move the initial operation prior to the training loop. This removes redundant computations across iterations and gives us significant speedups, especially in the training scenario. Now, to some of our evaluation results. We test on 4 GNN models: graph convolution network, graph attention network, graph isomorphism network, as well as graph sage. We test on a model configuration of 2 GNN layers with a hidden dimension sizes of 32. Our evaluations are on an NVIDIA H100 and A100 GPU, and we test against 4 baselines. One being DGL, which is maintained by AWS, Wisegraph, released last year, as well as C-Star and SPAS-DIR. We also test on a variety of data sets that span across multiple graph sizes, multiple input feature sizes, as well as multiple output class sizes. So here you see our main results. The x-axis shows various graphs as well as GNN models, while the y-axis shows the speed up of GALA compared to our baseline systems. So anything you see above here, above this red area, is a win for GALA. We achieve significant speedups overall, 2.55x, across all models, datasets, and baselines. So taking one of the more notable speedups that we observe here, the intra-operator transformation, tiled SPMM, gives a significant speedup when we are using the Reddit graph dataset. This, as well as the automatic operator reordering, which we do here, produces the same final result. Which again, the reordering still produces the same final result for this model, allows GALA to achieve significant speedups over other baselines. In addition to this, we conducted multiple other evaluations, such as a similar study for training, scalability studies, and how GALA behaves with different scheduling choices. We invite anyone who is interested to look up our paper for further details. So in summary, we present GALA, a GNN DSL compiler that achieves significant speedups over existing baselines through its language, IR, and automatic transformations. Thank you.
We are on time, so we have time for 2-3 questions for this talk.
Hello, great talk. Yeah, I'm sort of wondering, so it's really nice to have this orthogonalization of concern sort of between your inter-operator and intra-operator optimizations, but when you talk about the types of optimization choices that need to be made, a lot of these are inherently dependent on each other. So I kind of wonder, for the automatic transformations for this part of the kernel, how did you go about deciding about those? And have you, or would you consider evaluating against like the auto-scheduled version of Halide and Taco to see how the automation measures up against those?
That's a very interesting question. Our main evaluations are on, I guess, like a GPU, which makes sense because we are working with machine learning workloads. Taco, which I think like SPAS-DIR compress against, does better, so which is what we use for our baseline, which we have compared against and showed speedups. To answer, I guess, the first part of the question, sorry about this mix-up. Yes, these transformations, so the transformations that we considered so far are mainly focused on, can clearly be separated to the inter and intra-operator levels. There are transformations that do depend on one another, but we leave that as future work for now. But we can talk more offline if you're interested.
Yeah, for sure. Thank you.
Thank you. Is there more questions? If not, I have one question. Does the complexity of these networks affect how much you can optimize them?
To clarify, what do you mean by complexity?
Complexity can be, first of all, I assume that there are more layers, and I assume also that some networks can be, with much more nodes. So if this, did you observe any changes of the optimization to understand this relationship and be able to optimize depends on size?
Yeah, we did perform a scalability study, which is in the paper. In the interest of time, I couldn't present it, but feel free to look it up. But in summary, we see, we don't notice that much of a difference, and we see significant speedups even when the graph is even when the network is much more complex.
Yeah, that's cool. Thank you.
Yep.
We'll move to the next speaker. Thank you.